Very good morning, students. This is Dr. Rahim, which I am going to teach you the analog mixed signal for our MA VLSI design, unit number 5. This is our syllabus, which I am going to start analog VLSI design, small signal of MOSFET, and simple CMOS current meters, common source amplifier. We had three different types of amplifiers: common source amplifier, common gate amplifier, and common drain, that is known as source follower. So we had source degenerated current meter, cascode, and Wilson current meter. So we had three different types of amplifier, four different types of current meter with simple, cascode, and Wilson source degenerator. And then we had operational amplifier design and 6-bit flash ADC converter with high-speed comparators and thermometer code. This is I'm going to teach, and let me divide this into the three different sessions. First will be the small signal model, and immediately we'll followed with the three different types of amplifier. This is one section, and second section is nothing but simple CMOS current meter, and we had source degenerated current meter, cascode, and Wilson current meter. So this is second section, and third section is operation amplifier and 6-bit flash ADC, which I am going to follow with the comparators and thermometer to code converter. It is an internal part of the flash ADC. Let me tell you, in an external examination, you will find three different types of question. One will be definitely from amplifier, one from the current meter, and one from the op-amp design or 360 flash ADC is going to come. So approximately 15 to 20 marks definitely is going to come from your unit number 5, and this is very simple and easy. Let's start our this section. So I hope this is audible and clear. The first topic which I'm going to start is nothing but common source amplifier. Now look at it here. We had a transistor, so which you had gate, source, and drain. You had input is nothing but voltage across gate to source. Output is nothing but voltage across drain to source. So we can call VGS and VDS. Three different terminals. Normally it is a four different terminals because body source is not there. This is simple common source uh, like amplifier. So common source small signal analysis. So before going for small signal analysis, I had the same transistor which I am going to use for common source amplifier with resistive load. So we have used its gate, source, and drain. So here is your analog signal, and this is your DC signal. I am connecting drain across the output with load resistance. So when you have small signal and you had a little AC equivalent large signal is going to come. So when this is a normal circuit for common source amplifier, so a single transistor can also be an amplifier, but it is being connected with the load resistance. It is connected with the load resistance. So now I'm making as this is as common source amplifier with load resistance. If I convert it into the AC equivalent circuit, so the load resistance is being connected across the output. That's simple. So amplifier device which is given a small AC signal, and you will get a little large and AC signal. It is nothing but from millivolts to some huge microvolts of your input signal, small signal will be given to 180 degrees phase shift with millivolts of signal. So let's start with the DC analysis. This is your output characteristics of a normal MOSFET. You had x-axis your voltage across drain to source, and IDS is nothing but y-axis current to drain source. So when you're keeping VGS as a constant, you had three different characteristics. Like you had three different regions is going to come. This is your cutoff region. This is your saturation region. This will be a non-saturation region, or it is also called a linear region. So when you go to transfer characteristics, the minimum voltage required for to make your transistor is nothing but threshold voltage. At this point, the transistor starts operating. So that is your DC analysis of it. Now let us trying to understand little head when you are talking about the common source amplifier, right? So you need to look at some parameters which is already studied from your VLSI design perspective. Use nothing but you are had three important parameters which associate with the transistor. What are they? One is your transconductance, another one is that is called transconductance GM, and drain resistance RDS, and we can also have uh, amplification factor. So before going into the little more high, so I will start with the channel length modulation. So this is one of the important parameter, but it is nothing but 1 by lambda VDS. So for this, I had, as I said, that one parameter is nothing but RDS, resistor to drain source, is defined as change in the output voltage by change in input output current. So change in output voltage by change in output current. So a del change of VDS by del RDS. This is one of your RDS. So one of the parameter of your transistor. So we had 1 by RDS is nothing but your transconductance. So you can call like you can make it as like GM. So 1 by R is I can make is reverse of your del IDS by del VDS. So when you go for with respect to of this, you should have the saturation region equation. So with respect of IDS, saturation is nothing but mu n COX double by L VGS minus VT whole square by 2. This is your saturation. So what is channel length modulation? 1 plus lambda VDS. 1 plus lambda is nothing but you had lambda is your the variation where you can call VDS is nothing but effective voltage kind of. So either you can go for 1 plus lambda VDS, or else we can have VDS minus effective voltage. When you differentiate with respect of VDS in both the sides, so you will get it RDS is nothing but 1 by lambda VDS. This is your part of your RDS. So for this I had equivalent circuit for your common source. The input is nothing but voltage VGS, and you have current source we had GM by VGS, and GS, the trans conductance is different, and trans uh, uh, GS you had GM is nothing but trans conductance, you had GS is a conductance. So when you have reverse of your polarities, so VS, so 1 by RDS. This is the equivalent circuit for your common source amplifier. So when this part has been done, right, so it finally what you had common source amplifier question comes. First thing you have to remember with your this circuit diagram, and equivalent circuit is this. Equivalent circuit is this. So one of the parameters you had RDS. So just apply your KVL across this node. So what happened, what I required is nothing but IDS. IDS is nothing but GM VGS minus GS into VS plus VDS by RDS. So VDS by RDS. This is VDS by RDS. Now when I applied the KVL at this node, what happened? Your IDS is your output current. Output current is nothing but GM into VGS minus GS into VS plus VDS by RDS. So what is GM? So again you need to have GM transconductance. You had an equation of root of 2 mu n COX double by L into ID. Now ID is there. So ID is your drain current, current across drain source. So when I can write this GM as whenever take mu and COX double VGS minus VT whole square by 2. This is your IDS. All right. When you keep into this equation, what happened? It finally you get 2 ID by effective voltage. Just a small calculation. So VGS is not, but V effective is you can get it. So 2 GM I can write 2 into ID by V effective. You can write GMS. Now GS, when you compare GS is nothing but gamma GM in by root of VSB source to bulk plus 2 pi f. This is your Fermi level. So GS is written as this. So RDS you had 1 by lambda IDS. So it finally I could make the when you go for DC analysis, you had three things you need to do it. One is common source amplifier circuit diagram, then equivalent circuit. All right, what is RDS? You had three equation. One is RDS is nothing 1 by lambda VDS, GM is nothing but 2 into ID by effective, and GS is nothing but minus gamma GM by 2 root of VGS VSB plus 2 Fermi. This is your DC analysis. You have three equation, two circuit diagram. This is about the DC analysis. But when you go for AC analysis, so what happened? You had the same input is VGS. The circuit diagram is that your load resistance has taken on output. So VGS minus you had output voltage as it here your ID. So I can just make output voltage is equal to I into R. So what is I? You had IDS. You had IDS at here. You had IDS equal to minus of IDS into RL. Just a Ohm's law. So what is V out is nothing but IDS GM. So you had GM VGS into RL. How do you got this? You go previously you had an equation, you applied equivalent circuit of this. This ACNS equivalent circuit is this. So when you keep KVL across this node, you will get IDS GM VGS minus GS plus VS. So when you had source is across the ground, right? So source is this is your source which is across ground. So I can make this term as 0 minus GS into 0. GS into 0 is will be 0. All right. Something is 0 is nothing. You can neglect it. So RDS is very large. You can neglect that. So at output is nothing but V out equal to minus GM VGS into RL only. So what is gain? Output voltage by input voltage. V out by VGS equal to minus GM RL. So the gain of common source amplifier is nothing but AV equal to minus GM into RL. So what you can simply write for common source amplifier is nothing but circuit diagram, equivalent circuit, just make AC analysis, apply KVL, You will get gain of your common source amplifier is nothing but minus GM into RL, because here your VS is grounded, it has been neglected, RDS is very large, you can neglect of this. So GM is your transconductor, you already know GM, what is this? 2 into ID by effective voltage. That's it. Hence we can replace the resistor with the current mode in next one. So now I had done with common source amplifier with resistive loader. Now I am replacing with the current mirror. So before going for current mirror, so I am making in mix with two different, before going this topic of current mirror. So let's try to understand what is current mirror. So you had two different types of current mirror. Let me repeat. You had two different types of current mirrors. One is your NMOS source connected to ground. One is P source connected to supply. So I can say this NMOS current mirror as well as PMOS current mirror. So you had two different types, NMOS and PMOS. So what I'm trying to do is in this topic is nothing but in examination he might ask common source amplified resistance load. You can go with that. What is the gate? AB equal to minus GM into RL. But he might ask with your current mirror. So current mirror is nothing replicating of your the current with respect of the which is PMOS or NMOS. So you had two different types. Now here resistor load has been replaced with the PMOS current mirror at here. So this, because why we are replacing it here is nothing but there is a drawback, resistor or area. Note, very important point. Resistor will occupy more space in IC. We are replacing this resistor as a transistor level. So that's the reason we had current mirror. This is your active load of your current mirror. So which occupies very less space. So now you had PMOS. This is your PMOS current mirror which has been connected. Your current source, diode connected. This will be a diode connected. The current which is at here will be mirror across this PMOS. All right, this resistor is replaced with a normal PMOS and NMOS is there as usual. But here this diode connected terminal, this is shorted, source is shorted to your gate. So whatever the current at here will be mirror across this PMOS, your uh, up of your circuit. So that is your PMOS. All right. So you had at bottom you had NMOS. So I'm just using this PMOS current mirror. So as I said that two different types of PMOS. One is PMOS current mirror and MOS current mirror. So either one you can take off yours. So better you in your exam you take any one, not to both. So any one you can take and you can use of the current mirror. So I may recommend with the any one which normally I use the NMOS current mirror. What happened? NMOS current mirror you should use at bottom. PMOS current mirror you should use upper supply. All right, this is the only small difference with respect of that. So now we had done with this CMOS amplifier is connected with the CMOS uh, common source amplifier connected with the current mirror. So now let us go little head, try to understand uh, for your common source amplifier with the help of the current mirror. So as I said that you can use of both the things. I might be preferring it practically with the common source amplifier with NMOS, but you had any one you can use of. Let us go with, I'm going to teach you both the type. So I would, as practical person, I use of NMOS and current mirror for the CMOS common source amplifier. So first thing I'm going to show is common source amplifier with the PMOS as current mirror. So in exam he will not mention whether you take PMOS or NMOS. He will just ask common source amplifier with current mirror. You can take PMOS or NMOS. So this is my experience which I'm going to tell when I'm practical oriented. So I use of NMOS, but I'm going to teach you both it here. So this is your current source. This is your transistor of PMOS. This is your one more PMOS, and this is your NMOS. So common source is nothing but NMOS is that here input is applied across your gate, source is grounded, drain you have taken output. It this is your bottom circuit, and this is the upper circuit which is you have up you had PMOS, and PMOS is connected with the other PMOS. This I'm taking as Q2 transistor. This is diode connected Q3 transistor, which is source current source signal, which is current from here will be a mirror to this Q2. So that's the reason this is known as this is your circuit common source with current mirror. The equivalent circuit is at here. So input we had VGS. VGS is nothing but your voltage across gate to source, which is applied as an input voltage. So gate is there. Source has been connected ground. This is your drain. Drain terminals across the output. You had your current source VGS minus into GM. Along with that output side we had RDS, and parallel to the you had two resistors has been taken because your Q2 and Q1, Q2 and Q3. So I'm making a RDS, then two resistance, RDS1 and RDS2. So V out. Now what I need is V out. So what is output voltage for previous we had taken for common source is nothing but like output voltage by input voltage your gain is nothing but minus GM into RL. So RL is nothing but R out I am having. So here minus GM, R out minus GM is whatever we had it. These two are the connected in parallel. So AB is nothing minus GM into R2. This is very simple. This minus GM. When I was taking for the current source as common source amplifier with the NMOS current meter. So now look at the circuit diagram. The previous circuit as PMOS is up and NMOS is down. All right. So though this has been connected, you had this when you give a small input, you will get 180 degrees phase shift of your output. So same thing you had minus GM into R out. R out is nothing but RDS1 parallel to the RDS2. So this is when you look at NMOS and PMOS current mirror, either one you can use of it for that. So we had couple of amplifiers, the problems. So normally for your case, the problem will not come, but let us take one example for the calculate of your common source amplifier. So W by L ratio, which is given for your transistor is nothing but 100 micro W, and length is nothing 1.6 micrometer. So mu and Cux is your constant. So of your common source with 90 microamperes per meter. So mu and Cux for 30 microampere, I bus current has been given 100. So RDS is 8 800 8,000. So we had RDSP. So when you look at this substituted, we had the RDS1 and RDS2. We had GM formula. It's nothing but root of 2 ID mu and COX double by L. So just substitute, you will get GM. So your RDS1 and RDS2, your gain is nothing but minus 81.4. This is straightforward with current mirror with PMOS. Same thing we had NMOS. So you had Q1 and Q2 has been given when applied to it. When you are in PMOS, you had minus 81, and you had NMOS, you had minus 46.8. So keeping all the condition, the observation, we had common source with NMOS transistor and PMOS transistor gives higher gain. With NMOS transistor and PMOS load, current mirror will give higher gain. But compared to the common source amplifier with the PMOS transistor and NMOS current mirror. So you had observation when you look at the gain is a little higher, but when you had the stability, the upper transistor will be always be 2.5 times greater than the NMOS. So you had the NMOS mobility is more little more. So that's the reason we had the gain has been changed. So this is your common source amplifier with resist load, common source amplifier with the uh, uh, PMOS current mirror, and this is your common source amplifier with the NMOS current mirror. So I hope that the common source amplifier has been done till now. Next, we had it something called common drain amplifier. The next important, I hope that out of three amplifiers, you will get common source maximum. So we had one more amplifier that is called common drain amplifier. So it is also known as unity gain, or it can also known as source follower. So what is source follower is nothing but it's like a buffer. So you had driver, buffer, and buffer. What is buffer? Whatever you given it here, you will get it output. It's the same thing. So buffer is nothing but used for the impedance matching. Output is resistance should match with your the when you have multi stages, right? When I was trying to teach to you the same amount the language, you should understand. That was the matching. You if you understand, then the source of mine will match to you. That is called matching. If unable to understand by you is nothing but something called mismatch. So you had two different circuit. Let's take this circuit 1 and this is circuit 2. You had buffer, you had less circuit resistance is less, input output resistance less, and input resistance more less, and the output resistance more. So there is no impedance matching. So you should understand it. So for that we use of one more circuit called buffer. So it's nothing but improving of your matching response of it. So that's the reason we use take as common drain amplifier right here. So that is called unity gain. So now let's look at common drain amplifier. This is your circuit diagram. So you had NMOS current mirror right here, NMOS current mirror, and this is your AC equivalent circuit. Either you take DC or AC, but I would like to prefer because a small signal model. Whenever you talk, you just talk about amplifier only with AC equivalent circuit. All right. So we had this is your common drain amplifier. This is your AC equivalent circuit. So now let us Q1, Q2, and Q3 and Q4. So here is Q1. This is your NMOS. This is your also NMOS. This is your current mirror. So your output has been taken across your source. Previously the output common source has been taken for a source has been grounded, because source is common for that. Now drain is common for input and output. Previously source is common for input and output. Now drain is common for input and output. And now we had taken output from here, output side, and drain has been given as VDD. So your equivalent circuit is this VGS, and you have current source GM into VGS, and you have one more current source, you have GS into VACS and RDS2. So here RDS1 and RDS2. RDS2 has taken from your source. Now source from here, this will be acting as a resistor. Now this will be acting as one resistor, this will be acting as one more resistor. All right, this is your RDS1 Q1, this is RDS2 uh, Q2, and Q3 is nothing but diode connector. Whatever the current source at here, which will be mirrored to the Q2. All right, this is. Now let's try to make the analysis at here. So input voltage we are trying to give at here input across your Q1, which is applied to the gate. So V and input voltage is not equal to the VGS, voltage across gate to source. Then V out is nothing but VS1. So whatever V out at here, it will depends upon your VS1 is not the voltage source of your transistor 1. VGS1 is nothing but input voltage. What is VGS1? VGS2. So we had voltage across gate to source of second. So input voltage minus VS1. That is called voltage across gate to source of your Q2 transistor. So VGS1 is nothing but input voltage minus output voltage. VGS2 is nothing but input voltage minus voltage source of transistor 1 Q1. Let us take 1 by RDS is nothing but your GDS1, and 1 by RDS2 is nothing but GDS2. Now apply the KVL across your source side. So just apply your KVL across this source side at this point. Now what happened? Minus GM into VGS1 minus GM into VGS1 plus GS uh, into GS1 into VS1 plus VS my like you had 1 by RDS. So I can take of 1 by RDS is this plus 1 by RDS of 2. So when I was taking this, VS1 is there, VS1. So I can use of this part as a 0 and this part as a 0. So RDS1 and RDS2. So what I can write is nothing but, so it finally I can write VS1 is commonly taken GS1 plus GDS1 and plus GDS2. So here GM is nothing but VGS1, and GM is nothing but this when you are taking out this, because it has been GM, VGS it can be written as this part. So GM into V input voltage minus V out. So this is GS1, input voltage minus V out. So at finally V out I can write as GS1 plus GDS1 and GDS2 and GM1. And finally, I can write GM into V1. So output voltage is nothing but when all I was neglecting GM by 1 G11. So GS2 by GDS1 and GDS2 and GM. So this is your gain of your amplifier. And finally, I can write this when I was neglecting all these things. What will be happen? Output voltage of your amplifier of common source gate, common drain amplifier is nothing but unity follower, and source of your gain is nothing but gain AV equal to GM by 1 GN by 2. So I can this is a unity buffer which is having connected with common drain amplifier. So AV is nothing but GM1 by G12. So it will be almost equal to unity. So when I was at GS1 and GDS2 and GDS1 is the unity gain. So note I can write the common train amplifier has unity gain, very very high input impedance and very low output impedance. Hence, hence this used as a buffer. This used as a buffer, and also known as source follower. It is also known as output is taken at source and it follows the input due to the unity gain. So it is nothing but AV is nothing but GM1 by GM1 is nothing but similar equal to 1. So this is your circuit diagram, your NMOS current mirror and equivalent circuit. And finally, if you are not missing out of this, you can use of this final equation B out by Vn AV equal to GM1 by N GS1 plus GS2, and this can be it's very small compared to GM, so you can neglect this part. So at finally I can write GM1 by G1 equal to 1 similar. So this is, let us do one problem. So calculate the gain of source for follower assuming. So VSB equal to 2 volts, Fermi level is 0.35, and this gamma has become 0.5, W by L is 100, This is your mu and CY is constant at 90. This is mobility of NMOS. Mobility of PMOS is 30 microamperes by meter square, and I bias is 100, and RDS is nothing but this. When for this circuit diagram, so VAB is nothing but GM by GS. So what is GM? You had root of 2D 2ID mu and CY by WL. So whether you can use of GM1 is 1.06 MA. So GS is nothing but gamma GM by 2 of root of VSB plus 2 pi Fermi. So we had look at this equation in first starting, right? So it is nothing but 0.161. So overall, when you look at this, GDS1 is 1 by RDS. So 1 by RDS is nothing but RDS has been given at here. So RDS1, okay, RDSN, you had 8,000, and you had RDS N is nothing but, and we had 128K. So we had, this is nothing but similar to your GDS2. So you can write as 7.1 point kind of stuff. When you look at AV is nothing but it is 0.851. So it is approximately similar to the 1. So this equation has been proved in the previous of in the starting of our video. So according to that, the common drain amplifier is nothing but unity gain. So almost equal to 1, but it's not came 1, but almost equal to 1. So this is your second amplifier. When you compare to common source amplifier and common drain as known as source follower, unity buffer. So we had one more amplifier called common gate amplifier. So out of these three amplifiers, you will with resistive load or current mirror. So I'm using of current mirror, and you will get one in your external examination that can be the preferable for common source amplifier. So let us go for one more amplifier. So then we can take a break. So let's have one more amplifier right here. So that is called common gate amplifier. So now in this case, now you had previous case when you look at the circuit diagram, please try to mention the uh, common source amplifier circuit diagram different. So because source has been grounded, taken output from your drain. In common, just recall your common drain amplifier which is source follower, and source your output has taken from your source side, and drain has been connected to up. Now in this common gate amplifier, gate has been become as common at here. All right. This current meter is nothing but PMOS current meter. All right. So this current meter and output is taken from your drain. So here input has been applied across your gate, that is called V bias. All right. So source we had rose resistance, and you had given V input voltage Vs. So Vs will be something called input applied to the source to the resistor. So Rs voltage from the is taken from your. All right. So now DC output, DC voltage, that is your bias voltage is applied across your gate. This is your bias voltage applied across gate. That is your transistor one. This I can take in transistor one. This and Q2, and this is your Q3. Q3 is nothing but diode connector. Q3 2 is nothing but your PMOS. Um, and NMOS is nothing but if you have been using the same thing as an amplifier for that. All right. So in this case, what happens? V bias becomes the zero, and gate has been connected DC bias open in active region. Small signal model. So circuit is be common now. Gate is, if it is this gate is be common for it. All right. So and the circuit is said to be a common. So when DC out voltage is applied to the gate of your this transistor and operates in active region, in small signal model, V bias will be becomes zero. So I'm using PMOS as a current meter. So when you try to do the analysis, then you know you need to make this as AC equivalent circuit. So now let us look at AC equivalent circuit for this. So this is your AC equivalent. So you had VGS input voltage, gate is been connected at here, and source is at down, and then now gate is be a common for this. So you had GMVGS and GSVS and RDS1. This is your RDS1. You have load resistance. So this load resistance can be also be RDS2, that for the next stage. So at what we need is nothing but output voltage by input voltage. What we require, output voltage by input voltage. So gain is nothing but output voltage by input. The output voltage is this. Input voltage is nothing but VS1 into Vs1 by Vin. So I just Vs1 get cancelled, but output by input voltage is gain. But I need to apply, you need to have two conditions set here. V out by Vs1 is one condition, and Vs1 by V input voltage is nothing but one more condition. Now I am just applying out KVL across the V out by Vs1. So now I applied V out by Vs1, V out by this Vs1. So what will be the applying Kirchhoff current law across your V out at this point. So what we'll get it V out minus VS1 by RDS1, this RDS1 plus GM 1 into VGS minus the GS1 into VS plus V out minus 0 by load resistance is equal to 0. So this will be the GS1. Now I am trying to differentiate with applying KVL at here. I can write V out by uh, VS1 as the gain of it. So but GS is one small, right? So it finally I can make it the equation like the V out minus VS1. So RDS has taken it here 1 by RDS is like by GDS1 minus VS1 has taken as common. So GM1 plus GS Vs1 is will be as like gate to source voltage on plus V out 1 by RL is nothing but GL equal to 0. So I am using of GS is very smaller. So I am you can remove GS and GDS. So at V out by Vs1 it can be written as GM plus GS1 plus GDS1 by GL plus this GDS is coming at here. So if I take in this and negative 2, it finally I can write V out by Vs1 similar to GM by GL plus GDS when I apply the KVL across this V out. Same thing I had one more V out by Vs1. This is and now I had one more equation that would Vs1 by V in. Now I need to apply the KCL across the Q1 transistor. Q1 transistor is this. All right, apply it at this node. At this node, if I apply it here, so what I can write is KCL. Uh, uh, so you can write of your is minus GM. Now this will be flow minus GM into VGS plus GS uh, into VS1 plus V out. Uh, V out is nothing minus of V out plus VS1 by RDS equal to 0. All right, so this equation is like so minus okay we need to take minus 1, so minus is plus vs I am taking common gm1 plus gs1 plus gds 1 into plus v out into gds. So this gds is nothing but 1 by rds. The vs has been taken as common, so I can write gm1 gs this gs plus gds. All right, so it finally therefore I can write is. So when you go for voltage division or admittance, so it finally you can make of vs1 kind of. So you had two different equations at here. So you had two different divisions. So because of the resistance division rule, you had R1 and R2. So R1 R2 V out can be written Vn into R2 by R1 plus R2. So admittance I can take as Vs1 equal to Vm Gs by GL plus Gn. So this is about Gs and Gm is going to come. So we need to we need to find the input admittance, that is your Gm, that is your input resistance Rin. So Rin I can resistance 1 by Rin I can write as V by uh, R can be write as V by I, but 1 by Rin can be written as something called I by V. So is is there, so you had bs1. So after simplification you can make gm1 plus gs1 plus gds1 by 1 plus gds by gl. Substituting this in equation 1, you had this equation bs1 equal to input voltage into gs by gs plus gn1 and out bs1 by v in can be write as gs by gs plus gm1, that is your transconductance of your, and gs plus gs1 1 by gds by gl. So overall gain is nothing but AV V out by VS1 and play into VS1 by VN. So you had V out by VS is nothing but GM by GL plus GDS, and this VS1 is nothing but GS by GS plus GM1 by square. This is small, can be negative. It finally you can write overall gain for this is nothing but V out by VS1 or into VS by 1. So you can write it final equation as gain of your common gate amplifier is nothing but GS by GS plus GM by 1 plus GDS 1 by GL into GM 1 by GL plus GDS 2. So this is the end of your amplifier. So out of this amplifier, common source amplifier, common drain amplifier and common gate amplifier, more than 70% chances might be asking you common source amplifier. 20 to 30% chances having unity buffers, that is your common. So common gate amplifier is not used because of the complications of the AC equivalent circuit. So that's the reason I would like to prefer you to study only the amplifier of common source and common drain for your examination. So this is end of your amplifier. We'll meet in next section, that is your for the current mirror. I had three different current mirrors: simple current mirror, source degenerated, Wilson, and cascade. So four different current mirrors I'm going to show you. Out of these four, you will get at least one simple current mirror, and as well as any one current mirror is going to come for 5 marks. Thank you.